Friends, last we discussed about the equation of velocity and acceleration, and we also discussed about at which point of the path or the displacement the velocity and acceleration are maximum, and also we drew the graph of displacement versus time, velocity versus time, and acceleration versus time. Okay, after that, before this, during the simple harmonic motion, here the force is acting continuously on a particle performing the simple harmonic motion. This force is directly proportional to the displacement and also towards the direction of mean position. Right? We are going to derive the equation of this force, and that is the destroying force. Therefore, the question is that obtain force law for simple harmonic motion from the equation of displacement of simple harmonic motion. How we obtain the F is equal to minus kx, because in simple harmonic motion the F is directly proportional to the displacement at any instant of time and also in opposite direction of displacement. Therefore, F is equal to, here we take the constant kx. So that is known as the destroying force. That is known as the destroying force. We are interested to derive this equation. For that purpose, we start from, we accept the equation of displacement of a simple harmonic motion. For simple harmonic motion, the displacement of a particle at time t is, that is the xt is equal to a cos omega t plus phi. That is the equation 1. Now what's the amplitude omega, angular frequency? A equal to amplitude omega, angular frequency, and phi is equal to initial phase of oscillation. We know that the F is equal to ma, therefore the acceleration is required, so up to the acceleration we have to take the derivative of equation 1. Therefore, now differentiating equation 1 with respect to time t. Therefore, velocity vt is equal to d by dt of xt is equal to d by dt. Here, a cos omega t plus phi. Already we discussed about this derivative. Okay? For that purpose, A is taken constant derivative of cos omega t plus phi. Therefore, velocity at time t vt is equal to minus a omega sine omega t plus phi. Because the derivative of cosine with respect to time is sine. Sine omega t plus phi, and derivative of this bracket is omega. Therefore, as it is minus omega minus sine omega t plus phi into omega. Therefore, minus a omega sine omega t plus phi. That is our equation 2. Again, differentiating with time, with respect to time. So we obtain the acceleration at is equal to d by dt of velocity at time t is equal to d by dt. Here, minus a omega sine omega t plus phi. So it's equal to minus a omega common derivative of sine There is the cos omega t plus phi, and derivative of this bracket is omega. Therefore, minus a omega square cos omega t plus phi. That is the acceleration. But equation 1, a cos omega t. From equation 1, a t is equal to minus omega square xt. Minus omega square x. Clear this? Okay. But we know that, but from Newton's second law, there is equation number Newton's second law. F is equal to ma. F is equal to ma. Therefore, multiplying equation 3 both sides by m, so is equal to mat is equal to minus m omega square xt. But k is equal to m omega square. Therefore, f at time t is equal to minus kxt. Minus kxt. Therefore, force acting at any time t is directly proportional to the minus xt. Equation number. Thus, equation 4 is Paul's law for simple harmonic motion, which shows the strain force act on a simple harmonic oscillator is directly proportional to the displacement x and towards mean position. Towards mean position. So there is the first law for simple harmonic motion from the equation of the displacement. Nothing but only we have to first obtain the equation of acceleration, and after Newton's second law, F is equal to ma. Therefore, we are multiplying equation by m. Therefore, left hand side is F and this side is m omega square xt. Now listen here. The k is equal to m omega square. That is the wave vector. We discussed about this equation in chapter 15 waves. Right? Okay. Therefore, ft is equal to this. Clear this? Okay. No. Now, next question is that obtain equation of displacement from first law of simple harmonic motion. For that purpose, we start our discussion from the first law for simple harmonic motion. The equation is that first law for simple harmonic motion, F is equal to minus kxt. But we know that k is the wave vector, but k is equal to m omega square and F is equal to ma. Therefore, we can write like this way: mat is equal to minus k instead of the k, we write the m omega square x t. M cancel, therefore acceleration at is equal to minus omega square xt. Now we are interested to obtain the equation of xt. Clear or not? Because we are interested to obtain the displacement. Okay. Now, but xt is equal to a cos omega t plus phi. Therefore, acceleration at is equal to minus omega square a cos omega t plus phi. That is our equation number 2. That is our equation number 1. Now, integration or the integrating, taking integration on both sides of equation 2 with respect to time t. Therefore, integration a t into dt is equal to minus sign integration a omega square cos omega t plus phi into d. Already you learned about the integration in chapter 3 and 4. We are taking the integration on both sides. Therefore, integration dt on this side, left hand side, and integration dt on this side. Now, here the at is constant. Therefore, taken out. Integration of dt is equal to, on right hand side, minus a omega square is constant. Therefore, cos omega t plus phi into d. Now listen here, at as it is, integration of t is t only is equal to minus a omega square. Integration of cosine is sin omega t upon omega. So 1 times omega, omega cancel, and here there is the velocity and time t is equal to minus a omega sin omega t plus phi. The standard integration of cos theta is sin theta, and now here cos omega t plus phi, therefore sin omega t plus phi is the integration of cosine term, and integration of omega t is 1 upon omega. Okay. Now here velocity is equal to, or the acceleration is equal to, here we are using this concept, at is equal to velocity upon time. Therefore, acceleration into time is equal to velocity. So that is the equation of velocity. That is the equation number 3. Again taking integration with respect to time. Therefore, what's upon integration of vt into d is equal to minus integration a omega sin omega t plus phi into d. So here vt is common, integration of dt. Here minus a omega common, integration of sin omega t plus phi into d. Here dt as it is, integration of dt is only t is equal to minus a omega as it is, integration of sine, therefore there is a minus cos omega t plus phi upon integration of omega t plus phi is 1 upon omega. omega omega cancel, this minus becomes plus, and that is the xt. Xt is equal to a cos omega t plus phi. Is the equation of displacement. Equation number 4 is the equation of displacement of simple harmonic motion. Now, already we know that, and already we obtained the equation of the velocity in acceleration and also force law from the displacement. At the time, first we had done the equation of displacement and taking the derivative, we obtained the velocity. Taking the derivative of velocity, we obtained the acceleration, and we are applying the Newton's second law, F is equal to ma, we obtained the force law. Now here the reverse process. First we had done the force law for simple harmonic motion, F is equal to minus kxt. K is equal to m omega square. Therefore, F is equal to minus m omega square xt. Right? But F is equal to m. Therefore, m t is equal to m minus m omega square xt. M cancel. Therefore, acceleration at is equal to minus omega square xt. We substitute the value of displacement for simple harmonic motion, so it is equal to a cos omega t plus phi. Therefore, acceleration is at is equal to minus omega square a cos omega t plus phi. We are interested to obtain the equation of displacement from acceleration. Therefore, we are taking the integration on both sides of equation 2 with respect to time. Therefore, integration at into dt is equal to minus integration a omega square cos omega t plus phi into dt. A omega square is the constant, A is the amplitude, omega is the frequency. Taken out of this integration, so integration is. Now, integration of cos omega t plus phi is sin omega t plus phi, and integration of this bracket is 1 upon omega. On this side, integration of dt is only t, at into t is equal to minus a omega square sin omega t plus phi upon omega, omega 1 times cancel. Only we obtain minus a omega sin omega t plus phi. Now we know that acceleration is equal to velocity upon time. So velocity upon time into time, time can cancel, only velocity. So there is the equation of velocity. Again taking the integration with respect to time t. So integration dt dt is equal to minus a omega sin omega t plus phi dt. The same way vt common, here a omega common. Integration of sin omega t, there is the minus cos omega t plus phi, and integration of this bracket omega t plus phi is 1 upon omega. This minus minus plus, this omega omega cancel, only a cos omega t plus phi we obtain this side. Distance upon time or the displacement upon time is the velocity. Therefore, dt cancel, displacement xt is equal to a cos omega t plus phi is the equation of displacement of simple harmonic motion. Clear this? Okay, now our next question is that the equation of force law for simple harmonic motion, and obtain the equation of periodic time for simple harmonic motion. What is the period of oscillation? Right? We are interested to obtain the equation of the period of oscillation. For that purpose, for simple harmonic motion, the acceleration at is equal to minus omega square xt. Minus omega square x. Now for a simple harmonic motion, the acceleration of simple harmonic oscillator at time t is, that is the acceleration at time t is equal to minus omega square xt. Minus omega square x. Now, the force acting on the particle performing the simple harmonic oscillator is directly proportional to the displacement and toward the direction of mean position. Therefore, we are interested to obtain the equation of first the restoring force, and due to that result, multiplying both sides by m. Therefore, m80 is equal to minus m omega square xt. Right? From Newton's second law, the force act on particle performing simple harmonic motion is from Newton's second law, the first angular particle performing the simple harmonic motion is F is equal to m into AT is equal to minus m omega square xt. But we know that k is equal to m omega square. Therefore, F is equal to minus kxt. Minus kxt. That is equation 1. That is equation 2. Thus, the force act on the particle performing the simple harmonic motion is directly proportional to the displacement and towards the mean position. Therefore, F proportional to the minus x into here k is equal to m omega square. Therefore, omega square is equal to k upon m. Therefore, omega is equal to square root of k upon m. But omega is equal to 2 pi upon t. Therefore, 2 pi upon t is equal to under root of k upon m. Therefore, t is equal to 2 pi under root of m upon k. Actually here, t here, so t upon 2 pi upon under root k upon m. Now, inverse of this, therefore m upon is the equation of periodic time t for simple harmonic motion. So that represents the time interval of the periodic time for this oscillation. Clear this? Okay. Now again, how we obtain this equation? First, write the equation of force law for simple harmonic motion. Equation of the force law F is equal to minus kx. Right? So F is equal to minus kx. So first we write the For simple harmonic motion, the acceleration at is equal to minus omega square xt. So we are interested to write down this equation in terms of therefore multiplying both sides by mass. Therefore m at is equal to minus m omega square xt. From Newton's second law, the force act on a particle performing simple harmonic motion is F is equal to m at is equal to minus m omega square xt. But here the k is equal to m omega square, therefore F is equal to minus kxt. Thus the force act on a particle is directly proportional to its displacement and towards the mean position. And now we are comparing this k is equal to m omega square. Considering this equation, k is equal to m omega square, therefore omega square is equal to k by m. Therefore, taking the square root, omega is equal to under root of k upon m. But omega is equal to 2 pi upon p. Therefore, 2 pi upon p is equal to under root of k upon m. Therefore, t is equal to 2 pi under root of m upon k. This is the equation of the periodic time t for the simple harmonic motion. We are using this equation in practical to find out the force constant of a spring. Actually here k is the force constant, but the strain force per unit increase in length of a spring. Clear this thing? And here this equation F is equal to minus kx. F is equal to minus kx. K is the strain force per unit displacement. So here the K is the force constant. The strain force per unit displacement is known as the force constant. And what is the dimensional formula of this? Force constant. F is equal to minus kx. Therefore, k is equal to minus f upon h. The strain force per unit displacement is known as force constant. Force constant. Right? Therefore, SI unit of K is Newton per meter. Newton per meter. And dimensional formula of K is Newton M1 L1 T minus 2 upon L1. Therefore, M1 L0 T minus 2. And other unit is kg per second square from dimensional formula. So there is the dimensional formula of force constant, and also there is the SI unit of force constant. So that is important for one marks question. Frequently asked, what is the SI unit of force constant and dimensional formula of force constant? Kg per second square or Newton per meter or the M1 L0 T minus 2. Now just write down this equation. 1 upon f is equal to 2.5 d is equal to 3 by 2 minus 1 into 1 upon I1 minus 1 upon I2. Therefore, 2.5 is equal to 1.5 minus 1, that means the 0.5 into bracket 1 upon I1 minus 1 upon I2, equation 1. Now, for liquid, now this lens is immersed in a liquid. At that time, the 1 upon f dash is equal to, we have to find out the focal length for the new power 1 upon f dash is equal to, now listen, here the effective index of a lens glass with respect to liquid minus 1 upon I1 minus 1 upon I2. Now listen here, the important thing is NGL. NGL is equal to, now, NGL is equal to Ng upon NL. Ng upon NL. Now, Ng is given 3 by 2. Effective index of liquid is given 2. Therefore, 3 by 4. 3 by 4. Here, the most of the students make the mistake. Here, directly add down the effective index of liquid. But here, the effective index of glass in a liquid, that means with respect to liquid is 3 by 4. Now, initially, the glass is in A medium, therefore the effective index of a glass or the lens is equal to the effective index of a glass with respect to the A medium. Therefore, here 3 by 4 minus 1, we have 1 upon I1 minus 1 upon I2. So, we obtain the 1 by F dash. Now, taking the ratio, so directly I write down this equation. So 2.5 F dash is equal to 0.5 upon 0.25. 0.25 minus 0.25. Thus we obtain the 1 upon F dash is equal to minus 1.25 diopter. Minus 1.25 diopter. Now this numerical is important because the most of the students here make the mistake. In first part, when the lens is in A medium, at that time the effective index of a lens or the glass with respect to A is same as the effective index of a glass. So here the Nc minus 1, 3 by 2 minus 1, I1, I2 are not given. Now for the liquid, here the effective index of a lens or the glass with respect to liquid. So it obtained like this way, NGL is equal to Ng upon NL. So it's equal to 3 by 2 upon 2, it means 3 by 4. So this way we obtain the second equation. Therefore, taking the ratio of equation 1 to 2, so 22.5 upon 1 upon F dash, therefore 2.5 F dash is equal to, numerical is this, and 1 upon I1 minus 1 upon I2 is cancelled. Therefore, 1 upon F dash is equal to minus 1.25 diopter. That is the answer.